In this video, I'll be creating a board layout for a PCB, rendering a 3D CAD model of the finished PCB, and then sending it off to this video's sponsor, PCBWay, to have it manufactured. This is the final video in a 3-part tutorial series. If you haven't already, I'd recommend checking out the 2 previous videos on how to create an electronic component library, and then also how to create a schematic in Fusion 360. Picking up from the last video, to convert our schematic into a board, I'm going to go into the top left and select this button. And this will move us into the board layout menu of Fusion 360. Again, I'll start by just closing these side panels with the double arrows on the right and left. Down in this region, you can see the footprints for all our different components. And then this dark gray region represents the board footprint. The default measurements are 160 millimeters by 100 millimeters. My board won't need to be that large, so I'm going to reduce the size to 75 millimeters by 55 millimeters. To do this, I will go in and select one of the corners and then open up the inspector window again. And here I have the coordinate dimensions for the line. So it's going between these points. I want to change this from 100 down to 55, and I'll hit enter. And I'll go through and just change the rest of these as well. Next, like with the schematic, I'm going to turn on the grid lines down the bottom, setting display to on. I'll leave this at the default, and you can see all those grid lines. One important thing that I want to mention before proceeding is that the schematic file up the top and the board layout are dynamically linked together. So if you make a change to the schematic, say you add a new component or something, that's going to propagate over to the board layout. So in order to preserve that connection, you need to keep both files open at the same time. If I was to go and close the schematic file, we get this warning saying the schematic and PCB sync has been severed. And so any updates aren't going to be translated between the 2 files. So when you're working, you always want to have both files open. I'll go and open that file back up. To begin creating our board layout, I'm going to go back over to the Design tab and select the Move tool and move them around, and rotating them with a right click, and then place them somewhere on the board. So I'll put this one about there for the moment. It's a little hard for me to see these other components, so I'm actually going to change the background color. It's this light gray at the moment, but if I go up into the top, select my little icon logo and go to Preferences, then under Electronics, Color, yeah, so let's change this. What do I want to change? I guess it's the canvas color. Apply, yeah, so something a bit darker. That's pretty nice. I like that. Okay, now that we can see the components, I'll begin moving them around. As I'm moving the components around, you can see that there's these yellow wires. These wires are known as Airwires, and they represent the electrical connections between different components. For example, here we have a ground connection, and then up here we have a ground connection as well. And this yellow line is connecting them together. The nice thing about the Airwires is they're always optimizing the shortest path. So at the moment, this is the shortest ground connection here. But if I move this component to another area, yeah, so up here you can see the new closest ground connection is to this pin on that chip. So the aim with moving components around to begin with is to kind of cluster them together near where their neighbors are. So for example, I'm moving the potentiometers and the switch, all the input options, into one area down the bottom, and up the top I've got all the connections for the NeoPixel strips, and then over here I'll have some power regulation components and so forth. And that's going to minimize the amount of crossover action between the Airwires. We want to try and make it as clean as possible. You can see down here it's quite chaotic, but you can already see that up here, when the neighbors are clustered together, it immediately starts getting a bit cleaner and we can make easier connections. So go ahead and fast forward through this a bit. Now that everything's being rearranged, you can see how cleaner it looks. There's a whole lot less crossover between the different Airwires, and that's because everything is clustered together, as I mentioned. Before cementing the position of any of these components, I want to put the 4 mounting holes in each of the corners inset from the edge by 5 mm. So to do this, I could, manually move this to get to the position and try and place it accurately, but it's going to be a lot easier if I close that and open up the inspector window. And then just like when we were doing the board outline, if I click on the piece, I can give the exact coordinates. So the board width is 75 by 55. So if I put this at 70 mm and 50 mm, that's going to be 5 mm inset from the edge of the board. And I can go repeat that process for all these holes. Generally speaking, you'll need to experiment with component placement for a little while, figuring out what the optimal place for each component is. I kind of cheated doing this because I developed a board before I'm filming this recording, so I'm going to go ahead and just place all the components where I pre-planned the place. But it do take some time and kind of experiment around to find the optimal position that kind of minimizes the distance between neighboring connections. Now that I'm happy with the position of all the different components, I'm going to do a little bit of cleanup. So grab the delete tool. Then I'm just going to remove all this excess text that isn't needed. So for example, we don't really need to say that this is a potentiometer. It's just kind of self-evident by the component that goes in there. But we will leave the speed listing on there and the brightness because that's going to help differentiate between the two. Similarly, we don't really need to keep this component tag, the U16, U14. You could, if you wanted to, leave this component number, the diode number, but I'm going to get rid of it because we're only using one type of diode in this circuit. However, I am going to leave the 470 ohm and then the 10K resistance value because we want to differentiate between which components go where. But I'll go ahead and, for example, delete these ones. Okay, I'm pretty happy with how that's looking. So I have all the important values and information still on there. To give you a little sneak peek of behind the scenes, while I've been doing this on a second monitor, I've been referencing the final assembly board that I originally created. But looking at this final version is a good opportunity to start talking about the importance of layers in PCB design, as well as laying copper traces to make the connections. To view all the different layers on this final board, we can go to this drop-down menu here, and you can see there's a long list of different layers. So the top layer is represented in red, there's the bottom layer, which is represented in blue, and then some other ones as well, but we'll focus on just the top and bottom layer at the moment. This red color indicates all the copper connections on the top layer. So this is replacing the existing yellow air wires. So there's like a yellow air wire going from 5 volts here to 5 volts here, and I've replaced it with this copper trace going along here. A couple of tools that I'll introduce to you while we're looking at this finalized design is the toggle single layer view, which is going to isolate just the top layer. If we want to isolate a different layer, we can go to the drop-down menu here, which is a list of all the layers. And for example, I could select the bottom layer, and now the bottom layer is isolated. I can also flip the board, mirror it around. So one way or another, and top. And then one other one that I'll introduce you to, so I'll turn off the single layer view. So we've got all the layers. And then the final one that I'll introduce you to is the display button. And this shows all the different layers. You can see for the demonstration, I turned off the visibility on the T names, which is the top names, so the printed text on the top layer, and the bottom names, which is the printed text on the bottom layer. That's it's some documentation information. We'll get to that a little bit later. I kind of turned it off earlier just for visibility reasons. It gets a bit crowded when it's turned on. But I'll hide this away on my second monitor for now, and we'll go back to where we were. So we want to make copper connections between each of these yellow air wires. Zooming in, we have a couple of options to join together air wires. The first method is to route a manual trace, and to do this, I'll go up and select route manual, or you can click this one. Then say if I want to make this connection, this yellow air connection, I'll click one of the pads and just follow it along to make that connection. There are a couple options for the shape of air wires that can be made. So if I undo that one, you can see that I could also select one that's curvy. You know, you get pretty creative. And I can also change the trace width. Generally for signal lines, I go with a default value of 0.254 millimeters. And instead of these curvy lines, what I'll do is use the straight line with 45-degree bend. After I've placed the trace, if I'm not happy with the position of it, I can use the move tool to move the location of the trace. And if I want to remove a trace, then I can use the rip up tool to select a section of the trace, and that'll remove that section. A couple other options is, instead of just removing an individual section, I could go and rip up all the connected copper. So for example, click this and it removes all that connection there. There's a couple other ones here as well, so you can play with those. I drew this trace on the top layer as it's indicated in red, but like I said before, we can also draw them on the bottom layer. And to do that, I can click on the drop-down menu, select the bottom layer, and then I'll just route this Airwire underneath. So we have a top layer copper trace and a bottom layer copper trace. Sometimes when working on complex designs, you may run into a situation where you've painted yourself into a corner, and you can see I want to follow that yellow Airwire to make the connection over to this terminal, but this trace that I placed earlier is blocking my path. Now there is some ways to get around it. You know, I could go around, do some other stuff, but another option I have is to go underneath using a via. So if I click the center scroll button on my mouse, this green dot comes up, which is a via, and that makes a connection through the board to the underside. And so the trace is now on the bottom half of the board and it's in blue, so it's passing underneath that red wire. And then I can come up to the top again by just pressing the center button on my mouse, placing that, and you can see the connection is on the top surface. There are also some options for changing the size of the via, so you can change the diameter and such. I generally just leave it at the default values though. If you don't want to manually place all these traces, then you can also opt to use the Autorouter underneath the quick route. The Autorouter down the bottom here is a tool that will automatically test out lots of different layouts for your traces to find one that makes all the connections between your components. So to do this, I can click continue. You can also choose the amount of effort that it puts into it. So if it puts in a high effort, it's going to take a longer time to do the computation. But I'll go ahead and continue. This isn't a very complex board design. And then I'll start running it. And you can see it's testing out lots of different ones. It's found one that it's pretty happy with. There's a few other options that I could select. So this makes PCB board layout very quick. However, there is some limitations to using the Autorouter. In particular, it's not able to optimize the location placement of the components. You can see it didn't test out moving the components around, it just left them where I already had them placed. If I move these components around, I may actually be able to find a more optimized solution. And it doesn't really care about the overall aesthetic value of the traces. You know, it doesn't try and beautify your board layout at all. I'm not going to get up on a high horse and say never to use the Autorouter, especially because my trace layout is far from optimal or graceful in and of itself. But the general consensus amongst the electrical engineering community is that manually laying traces is almost always superior compared to using the Autorouter because of the reasons I mentioned regarding component placement, complexity, and overall aesthetics. So I'll go ahead and undo what the Autorouter just did for me and continue manually placing the traces. To be honest, I actually find laying the traces manually to be the best part of designing a PCB. It's a problem-solving challenge similar to something that you might find in a newspaper, like a game of Sudoku or a crossword puzzle. I've now made connections for all the different signal trace lines, and the only remaining air wires, these yellow wires, are the 5-volt and ground power lines. But before getting to that, I want to address using DRC, or design rule checks. If we go up to the top and select the rules DRC ERC tab, and then hit the DRC, the design rule check. This is a list of rules that the editor will check to ensure that the final PCB design works correctly. I can toggle through the tabs up the top here, and it gives me different settings, different tolerances for different dimensions within the board. So for example, here we have the distance between the edge of the board, this gray line, and then different holes and components. If you change any of these settings, you can just hit apply and then check for any rule violations here. So you can see I get a lot of warnings saying that I have Airwires, not connected, which at the moment, yeah, that's pretty obvious. But for example, if I tried violating one of these rules, let's say I go back to design and I rip up this connection here, and then I make a new trace. If I try going past the edge of the board, if you recall, we said that the minimum distance between a trace and the edge of the board, I think, was 40 mils, and we can't get any closer than this to the edge of the board. Similarly, I can't get too close to a pad here, and then also to other wires, like it tries to push it out of the way, but I can't cross over it. When we're finally finished with our design in a few minutes, we'll run this DRC check again, and then hopefully when we do that, we won't have any errors because we will have made all these Airwire connections go away. So let's make these traces for the power connections. The reason I haven't already made these connections is that these power lines are going to be high current connections. While it's not important for all PCB designs, for my specific application, this board needs to be able to deliver around 10 amps of current. However, if I tried to ram 10 amps of current through one of these thin 0.254 millimeter traces, then it would heat up until the connection literally burnt away. As such, for the 5-volt and ground connections, we need to use much thicker traces. But the question is, how thick is thick enough? Fortunately, we can use an online calculator tool like this one provided by DigiKey. We can enter in our parameters, so I want a trace that's capable of handling 10 amps of current. The second value here describes the thickness of copper on the PCB in a density measurement of ounce per foot squared. The standard thickness for most PCB manufacturers is 1 ounce, so I'll go ahead and enter that. And let's say we want a maximum temperature rise of the copper to be 15 degrees Celsius above the ambient room temperature, 15. These last two variables aren't important to determining the trace width, so I'll ignore them. On the right, this is the values created by the calculator. I'm going to change it to millimeters and change this one to millimeters as well. So if we wanted to use an internal trace, which means it's between the layers of the board, we would need a width of 14.6 millimeters, which is massive. However, since we're only doing a 2-layer board and our traces are going to be on the surface of the PCB, not inside the PCB, we can get away with a much thinner trace of 5.6 millimeters. And that's because it's in contact with the air, so that heat dissipates quickly. This is still pretty thick, so to avoid this, we could change the thickness of copper to, let's say, 2 ounces, and then you can see the width of that trace drops down to 2.8 millimeters, which is a bit more reasonable. But the trade-off here is that the thicker copper is going to increase manufacturing cost. One easy workaround is to use a trace on both the bottom and top layer while leaving the copper thickness at 1 ounce. By doing this, we're still fabricating at a low cost, but because there's copper on both sides, we effectively are doubling the copper thickness to 2 ounces instead of 1 ounce. Back in Fusion 360, now that we know we want a trace thickness of at least 2.8 millimeters on both sides of the board, I can go down and change the width, and I'll do 2.8. Actually, I'll increase this just to be safe, so 3.25. You see there isn't much room for this, but we'll make it work. And then we also want to repeat that pattern on the bottom layer as well, so we're doubling up the thickness. And I'll go through and connect all these 5-volt lines together on both sides. The 5-volt trace is only one part of the equation. The ground trace also needs to be able to dissipate just as much heat because it'll also be carrying 10 amps of power through it. We could create another set of fat traces like this. However, we have the alternative option of creating what is known as a ground plane. A ground plane is a flooding of copper on one or both sides of the PCB that fills in all the empty spaces between the trace lines. So these big splotches of color are all ground. Since every component needs to connect to ground, it reduces the number of traces we need to draw. To create this ground plane, I'll hide away this finished example and go back to our current one. To create a ground plane, I'm going to right click on the edge of the board outline and then select Convert to Polygon, and I want to copy it instead of replace it. And for the top layer ground pour, I'll select the top. For the next one, we'll select bottom. And you can see this automatically fills in all red, all that extra area. If we use the inspector tool and select the polygon, we can see that at the moment it just has an arbitrary name, but I'm going to convert this to ground. And when I hit enter, just watch what happens to these pads here. So I'll press enter now. Oh, yes. And you can see that it's now connected to ground, and all those ground air wires have disappeared. So Command Z, you can see that there's the yellow wires. They still need to be connected together, and then redo that. And now they're all connected through this ground plane. I'm going to make a couple of changes here, again using the inspector tool to select the border outline. I want to change the width of these connections, make them a bit wider, let's say 0.8. And then I'm going to change the width of the overall pour to something larger, I don't know, 0.6 or so. Yeah, that's just going to kind of round it off a little bit on the edges there. You can see all the ground connections are now made through this polygon pour. Due to the layout of my board though, if you actually trace this area, you can see that the ground makes connections up through here, down here, but in this section it gets blocked off here. It's able to come through here, but it's kind of constrained to this region. So this area of the ground plane is isolated from this area of the ground plane, and that's indicated by these yellow air wires here. There's no connections between this section and this section. So a couple ways to get around this is maybe I'll rip up this one. It's a pretty narrow passage there, so I'm going to move this trace over this way and just make that a little bit thicker there. The top layer is looking a lot better now. It has two paths that can go. There's up through here and then over this way, or it can go through here and over that way. And there's a bridge there as well. And we'll repeat this process creating a ground plane for the bottom layer. This time we want it on the bottom. Okay, and then same process again. We're going to change this to ground. Yep. The bottom layer, the grounds, you can see there, there's nice connections all through here. There's good space for all the power to distribute through here. More for up going through here and powering this LED. Now that all the copper's been laid down, let's go and check if we've made any mistakes. So using the design rule check, run the DRC, and check. Oh, we have one error. So there's a clearance. What's that? Oh, okay, yep. So here, this blue wire is too close to this pad. So yeah, it's just a bit tight there. So I'll just use the move tool and move that out a little bit, somewhere in the middle. Okay. And now when I run it, we're all good. At least we should be. Yep, and the bottom, no errors. DRC, no errors. It's a personal preference, but I kind of find these ground pour planes a bit overwhelming. So you can turn them off. I'll go to polygon and then hide the polygon pour fills. And that just makes it a bit more visible. You'll notice that the ground connections are still connected together. It's just not explicitly shown. I think it just looks a bit cleaner when you're working on the board. Lastly, we want to add information and a bit of documentation to the board for reference. As you can see, I already have various components listed with their values, like these resistors and the capacitor. But on the back side of the board, I want to add some reference information to the Silkscreen regarding current ratings, as well as a URL to the documentation. To add this additional information, I'll go up to the Document tab, select Draw Text, and I'll type in a little blurb. The moment I've the bottom layer selected, but I actually want this to be B names for bottom names. And I'll flip the board, there you go, and put it somewhere around there. I can format the position a little bit later. Okay, this one I'm just going to copy and paste the text from my previous design. Let's place that, yeah, somewhere around there. So I'm pretty happy with the board how it is right now, and we can go ahead and manufacture it. But before doing so, I just want to have a preview and see what a 3D model of this board will look like when it's assembled. So going up here, I can click on the Push to 3D PCB. And there we have it, a 3D model of our PCB. I can go underneath and you can see the documentation that we just added. If I want to see the PCB just by itself, I can go and hide these packages. And yeah, that looks pretty good. I'm pretty happy with that. So to fabricate this, I'll head back to the file where we did the PCB board layout and head over to the Manufacturing tab. We can click on CAM Preview. This gives a similar view of what the final board will look like, just a 2D bird's eye view. Bottom side looks pretty good. To move to the next step, I'll click CAM. This CAM processor window is a tool to convert our design into a Gerber file. Gerber files are the standard for PCB designs containing all the information. This is where all the copper on the top layer will be poured, on the bottom layer, overall board layout. Yeah, you just keep toggling through all the different things. You can see all the text that we've got there, the solder mask, and so forth. I'm going to want to export this as zip, so click that, and then Process Job. Quickly save it. Okay. To get the board fabricated, I'll head over to PCBWay, which is a PCB fabrication service that I regularly use, but is also the sponsor of this video. PCBWay offers an amazing service for quickly manufacturing high quality and affordable PCBs. To fabricate my design, I'll click on Quote Now, then choose Quick Order PCB. Here I can upload my Gerber file, choose the zip file that was just created. There are a number of different parameters that we can adjust, such as the board thickness, the material that it's made out of, the color of the board, and so forth. If it's your first time designing a PCB, don't worry, you can just leave all of these at the default settings. They'll work perfectly. And then we can go ahead and order the board. You can see that for only $5 plus shipping costs, I'll get 5 PCBs quickly delivered to me. If you're watching this tutorial, I'm sure you have a PCB in mind that you want to fabricate. So when you're ready, head over to PCBWay to bring your design to life. Now that I have the PCBs, I'm ready to assemble the circuit. It's a pretty straightforward case of soldering the components and uploading my code. If you want, you can check out the sample code on GitHub, or if you haven't seen it already, you can check out this video where I use this exact PCB to modify the side panel of my computer to create the raining code animation from the matrix.